Hey, science research. Hope you guys are doing well. This is the next part of our protein unit. This is protein crystallography. And in this slideshow, I'm going to explain a little bit about how we grow proteins, why we grow proteins, and the whole point of analyzing them. As you can probably tell already, I love proteins. Totally science nerd, what can I say? But proteins really are responsible for so many things in our lives. For example, right now with this COVID-19 virus, there's been a tremendous amount of research into what's called the spike protein, which is on the outside of the viral particles. And scientists have identified the structure of it. They've actually done crystallography on this protein. And so we know exactly what this protein looks like. And now we can start to develop vaccines and treatments that can help block those particular proteins. And we'll talk about that a little bit in another segment. But that's just one of the examples of the importance of crystallography. And actually, right now at Brookhaven National Lab, all research work has ceased, with the exception of work focused on looking at the structure of the virus. So it's pretty important stuff going on, and protein crystallography is a huge field. Um, so basically, the way it works is you want to grow protein crystals. So these are crystals of a protein that is known as MyAB. This comes from a bacteria known as Mycobacterium abscessus. And this is a protein that's known as a TRMD protein. It stands for tRNA methyltransferase. And basically, each one of those little crystals contains millions of small units of this individual protein. And these crystals, in their shape that they're in, we can analyze the structure of the protein in those crystals. So this particular protein is involved in, let's see, this is Mycobacterium abscessus. This is involved in infections of some humans from surfaces. So this is a surface bacteria that can produce these infections. Here's another close-up look at, just get rid of that thing. There we go. Here's another close-up look at these. You can see they're beautiful looking crystals. There's some little smaller fragments here. But if you notice how they have different colors to them, when we look at proteins under the microscope, one of the things that we want to do is put it under a little piece of diffraction grating, which allows the light to polarize. Protein crystals will polarize, and we will see different colors because of this polarization. Now, to set up a protein, what you need to do in order to grow crystals is you have to put them in a tray. And so the tray would have a particular setup to it. And on the side of the tray, we always label it with our name, the protein, what are we using, and what's the date. Okay. This is what a typical protein tray looks like. This happens to be a tray for what's known as a hanging drop tray. There are wells. This happens to be a 24 well tray. And those wells are where we would put different combinations of chemicals. We would refer to that as our buffer. And so we would put those in those trays, and each well is marked with a letter and number designation. So you can see A1, A2, A3, A4, A5, and A6 across the top. Bottom row, this would be D1, D2, D3, D4, D5, and D6. Okay, so that's what's known as a hanging drop tray. And basically what you do is you add your solution of crystallization compounds to the well. Now, normally what we would do is we would add, let's say, 1,000 microliters of this to the well. The tricky part is now the slide. There's a little cover slip slide. It's made out of silicon, and it goes over the top of this, and it covers the well. And so what you would do is pipette your enzyme onto this. You'd make a small drop of enzyme. In this case, we're using lysozyme. And you would mix 5 microliters, let's say, of the enzyme with 5 microliters of what's in this well solution. Okay, the idea is that you have a very high concentration of solution here, and the trick is to get the solution from here to diffuse down into the reservoir solution. Okay, and in doing so, it forces a crystal to form. Okay, so once you have that drop on there, you pop it on the top of this well. Now there's a little bit of grease that's on top of these, kind of like a Vaseline, and that seals it. It keeps it airtight so that this liquid doesn't evaporate. And what will happen is vapor will diffuse. You'll see vapor diffusion going on, okay? And the idea is that whatever liquid is in this drop is going to diffuse into this reservoir solution, and it's going to force crystals to grow in that little drop, okay? Sitting drop is another method, works the same way. The difference is instead of the drop going on your cover slip, the drop goes on this little post, and there's a little depression in here that the reagent and the protein sit in. And the idea is that the water will diffuse out of this into the reagent, and it will force crystals to develop inside of this drop. Now, how do you get crystals to form? It's all trial and error. You basically play around with concentrations. You change around the ratio of reagent and protein. So, like for example, in that first slide, we said 5 microliters and 5 microliters. Maybe on another one, you do 5 and 10. And then on another one, you do 10 and 5. And then in another set, you could say, okay, let's do 5 microliters of reagent, and let's cut the protein down by half and do like 2.5. So you can play around with different concentrations. And the idea is through trial and error, you try to develop the best crystallization conditions so that you can grow what look like the nicest crystals. Okay. I'm backing up. I don't know why. There we go. This is what the sitting drop tray looks like. And you can see in the sitting drop tray, you have that tiny little stalk on the top, that little post. And in here is where you would put the drop of the liquid that contains the protein. And then from the reservoir, right, from the surrounding reservoir, you would take some of that and put it in there as well. Okay. When you do this, you get a crystal. And you harvest the crystals. We fish them out using these little microscopic loops. The loop is basically made out of a monofilament, kind of like fishing line. And the goal of this is that you scoop the crystal, right? Here's the crystal right here. You scoop it up with this loop, and sometimes other junk gets in there too. And then you quickly freeze it. So this is a crystal that's actually frozen. And this is the surrounding solution, right, that the crystal was frozen in. Okay, we freeze them in liquid nitrogen. It's really neat. And then what we do is we take that crystal and we mount it to the synchrotron beam line. And that's where we can analyze the data. Okay. So that single crystal, again, we can form a diffraction pattern from that crystal, and then we can look at the electron density and develop a model of the protein. Okay, so a little bit about synchrotron radiation. Some of you guys saw this presentation from the other day if you participated in the NSLS data analysis. Some of you were interested in doing that, so I had sent an invite out to those that were interested. But basically what synchrotron radiation is it's a microscope. A synchrotron is basically a gigantic microscope, and we use light energy to magnify what we're looking at. So the National Synchrotron Light Source 2, NSLS-2, is at Brookhaven National Lab. It's tremendous. You can actually see it from space, from a satellite. Okay, and so here's NSLS-2, and here's the RIC, by the way. That's the Relativistic Heavy Ion Collider. This building is large enough that Yankee Stadium can actually fit in this inner space over here. Okay. Now, basically what a synchrotron is, it's a large ring of magnets that propel electrons to almost the speed of light. And when you do this, these electrons begin to emit energy in the form of X-rays. Okay. And this building is set up with 4 different what are called LOBs, lab office buildings. We do most of our work at LOB 745, okay, and that's where we have our lab set up and our equipment and what's known as the beamline end station, okay. So how does the synchrotron work? Well, basically what you do is you take electrons and accelerate them in this curved path using magnets. Usually in the inside of a synchrotron, you have what's known as a booster ring, okay? And the booster ring is where you get these electrons to move faster and faster towards the speed of light. And we use magnets to do this. Okay, so there are very strong electromagnets that have different types of polarity that accelerate these electrons. Now, to inject the electrons in, you basically use what's the equivalent to a gigantic spark plug. It's known as a linear accelerator. Excuse me. And it's linear because it's just long. So this is the linear accelerator here, right? It's known as a LINAC. And there's a gun, quote unquote gun, that they use to release electrons. And you can see from here, it's made of tungsten. They heat it to 1600 degrees, and that causes electrons to get released. Once these electrons get up to the speed that we want them to be, to the velocity that we want them to be, they are then injected into the ring, and then these electrons just consistently circle around this ring. Now, what makes them emit X-rays is that at each point, it's not a true circle. It's actually a ring set up with multiple angles within it, so it looks like a ring. So at each turn, when the electrons turn, they slow down a bit. And as they slow down, they release energy in the form of X-rays. And then those X-rays get captured in a small lead tube, which funnels the light down into what's known as a beamline end station. Okay, and this is where we have all of our experimental equipment. Okay, so again, the idea is to harness this X-ray X-ray energy, and utilize that light energy so that we can analyze different types of compounds. Okay, now this light energy starts off as X-ray energy, but there are many ways to kind of tame the energy down and absorb certain wavelengths so that we can use what's known as higher energy X-rays. We can use what's known as soft X-rays. We can use tender X-rays, which are very low energy X-rays. And those have different types of applications. We can even take this X-ray energy and modify it so that we wind up just getting UV out of it. So there are many different ways that we can harness energy from a synchrotron. Okay, but it's all about light. Okay, now the idea with synchrotron radiation is it's a very narrow beam of light, so it's very focused. Okay, it doesn't spread out like a light bulb. It's extremely bright. Okay, it has quite a bit of intensity to it. And we can also vary the wavelengths. Now, the idea with the NSLS2 was that it gave us an even brighter light. It gives us more energy coming in, and it allows us to do even more in a shorter period of time. So one of the beauties of this is that this light energy can be used for many different applications. Okay, it's a higher intensity. We get better resolution out of it. And you also have what's known as tunability. We can adjust the wavelength coming in by using all kinds of different adjustment techniques. So this is what the synchrotrons actually look like. So in the upper left corner, these are the magnets that help accelerate and propel the electrons. These magnets, the white part here is the actual magnet. So some of these you'll have 6 magnets in a circle, some of them have 5, some of them have 4, and it all depends upon what's happening with the movement of the electrons. Okay, but they generally move through this lead tube through these magnets, and these help to move it along. You can also see here in this bottom picture, these are magnets that are set up slightly differently than the ones in the upper left. These are long magnets that sit on the top and the bottom of the tube, and there are also magnets that are on the sides, and those help bend the electrons as they're moving through. Some of these magnets, they have some cool names. They're called wigglers and undulators, which literally force the electrons to move within their space and emit energy. Okay, now this is very powerful energy, and so this particular portion of the ring is behind walls that are made of concrete and lead. And at the top right here, this is one of the beam lines. These are lead doors. These are solid lead. They're actually on these tracks. They can open and close electrically. And then this wall here is made up of lead as well to protect users from any X-ray exposure. Okay, so basically what you need to build beam lines, you have to have your source coming in, right? We have these tiny little slits. These slits allow the energy to come through in a focused beam. So instead of it just being this big, bright, diffuse light energy, this helps to make the light energy come through in a specific focus point. We have what is called a collimating mirror, and that helps to reflect the light energy. And then we have what are called monochromators. And these monochromators, what they do is they help to focus the energy down to specific wavelengths. So we can use these for specific wavelengths that we want, right? When we're looking at proteins, we want to have a certain wavelength of energy coming in. These monochromators allow us to reduce and alternate the energy so that we have the specific wavelength in terms of nanometers coming in, what we want. And then we have additional slits, and we have refocusing mirrors, which help guide the light beam specifically to the target that we want. Okay, so a lot goes into building these. Not all beam lines have all the same components. This is what FMX and AMX optics hutches look like. You can see here, this is the tube where the beam comes in. So the beam comes down from the main ring through this wall, and within these boxes here, these contain mirrors and focusing equipment and monochromators and all kinds of equipment that helps to focus the beam energy, change the wavelength, and give us the exact energy that we need. Okay. What we have in our beam lines are two robots. This green robot is known as Kermit because it's green. And what this robot does is it automatically loads our protein samples. So at the end of this robot is a small little magnetic tube that can go and pick up each individual protein sample. And then it mounts it right here in what's known as the cryostream. And the beam of X-rays comes from behind this unit here, and the X-rays come out and hit our sample right here. And then those X-rays cause the electrons in our protein to diffract, and those electrons diffract, and it gets captured by this machine right here. Now this machine's way back. Usually this is up close, so it can pick up and detect the electrons. So this is the detector that's actually picking up the electrons. And when it picks up those electrons, it converts those electrons into what's known as a diffraction pattern. Okay, so we are doing this using what's called single crystal diffraction. So further down the line, this is the other robot. This is called Big Bird. This Big Bird is yellow. And up close, you can actually see what Big Bird does is it will mount our sample. This is what's known as a pin and a cap. And at the tip of this pin, we have our small little loop, and that's where our protein is. So the protein is actually right here at the end of this loop. The X-rays are coming in and hitting our protein. They're coming in from here. This way they hit the protein. We have a camera on here so we can see what we're doing up close. And that camera allows us to take this and rotate it and position it exactly the way we need it to be. And so all of this is automated. And what we do is we sit outside of this hutch that all of these machines are enclosed in. And we can use the computer to manipulate and move our samples and collect the data as we need to. And all of you, if you're interested in doing this, will be trained and learn how to do this. And you'll actually drive, quote unquote, drive the equipment and drive the beam line. Okay. There is no crystallography without crystal. That's from one of our mentors, Dr. Vivian Stojanov. Crystals are beautiful. They're gorgeous. They have all kinds of colors to them. And ultimately, what we want to do is take our crystals, get the X-ray diffraction pattern, which we have an example here, and then determine what the structure of the protein looks like using data analysis. Okay. So just to summarize, X-rays come in, they hit our sample on the cryo loop. The sample diffracts, and we see these electron patterns form. That's what the detector picks up. Once the detector picks up that pattern, we can then use that information and that data to start building a structure of the protein. We can figure out where all the different molecules in our protein are located and ultimately develop a three-dimensional structure of our protein. And we, of course, refine it down. This is what it looks like when it's rough. And then as we continue to work on the model and refine it and pinpoint exact locations of atoms, we get a complete structure of a protein. Okay, this is a picture of what diffraction actually looks like. This is taken from the beam line that we were at a few months back. And you can actually see this pattern. Each of these dots, oops, I'm sorry about that. Each of these dots represents electrons. We can look at this pattern to determine, hey, this is a good pattern, this is a bad pattern. This bright ring here is known as an ice ring. So there's a little bit of ice in here. And you get ice because you're freezing things. When we freeze with liquid nitrogen, any water in our solution is going to turn to ice. So we actually have to protect our protein. So before we ever freeze a protein, we add antifreeze to it, either ethylene glycol, which is antifreeze that's used in cars, but we use a purified form of it, or glycerol. And Glycerol and ethylene glycol, they are excellent compounds to use to inhibit ice formation. We don't want to get ice crystals. Now, what do protein crystals look like in the loop? They look like this. And what we have here is a grid over it. It's known as a raster grid. And this allows us to identify parts of our protein that look like they have good X-ray diffraction data. So the computer actually detects where there's good diffraction after we've hit it with the X-rays, and we're able to identify the structure of the protein. Once we've collected all the data, the next step to this is analyzing it and trying to figure out what our protein looks like. So inside of this little cube, okay, which happens to be, this might be just a salt cube or insulin, but inside this cube of protein, there are millions of small little protein structures and protein molecules. And when we hit these with the X-ray gives us a diffraction pattern that tells us what the structure looks like. And that is what we ultimately plan to do. We've already done this with one protein. You guys have heard me talk about the anaprotein from anaplasmosis. Anaplasma phagocytophyllum, and that we have identified a structure that is complete that does not have its normal ligand, which is a reactive compound inside of it. And so that is being published. And so that's the paper that Chris and Damien and their counterpart Danielle over in Northport have been working on. We have many other proteins that are not yet published and have not had their structures determined. And so the whole point of me showing this to you guys and teaching you guys this is so that we can have another group join this collaboration and work on additional proteins with the goal of identifying structures, depositing them into what's known as the protein data bank, which I will show to you guys, and then ultimately publishing a paper. So that's really my goal and my hope for you guys, and that's really where all this is going. So if this is something that you're interested in doing, what I will be doing in the next couple of weeks is figuring out, because we have, everything's remote right now, how to get you all set up for this. Sorry about that. How to get you all set up for this. So I will be discussing this with B&L, and I will let you know what else we need to do. But that's it for protein crystallography. I hope this makes sense. The next step we're going to do is we're going to look at JMOL. And JMOL is basically taking the data from a beamline like this, where it's all been processed, and looking at the protein structure. Okay? So I hope you guys are doing well. Stay healthy, stay safe, and I will